The next step from simple harmonic motion is to talk about waves. And waves are generally caused by some type of simple harmonic motion, so it's kind of a natural progression to move into them after addressing simple harmonic motion. A wave is simply a disturbance that travels through a medium if we're talking about mechanical waves, or with electromagnetic waves. It can be a vacuum, and just for clarification, this EM here does stand for electromagnetic and will in the future. Waves transfer energy and momentum from one place to another, and the direction of that energy transfer is the same as the direction that the wave is propagating. And when we talk about this term propagation, we're simply talking about the direction that the wave is traveling. The important aspect of wave propagation is that the energy moves in the direction of propagation, but the medium itself does not have any net displacement. It oscillates back and forth in a particular direction, but it's not actually transferred in the direction the wave is moving. It really ends up staying about the same spot. When we're talking about waves, we can talk about wave pulses. And a wave pulse is a quick distortion or disturbance that travels through a medium. And to show you that, let's go here real quick. And you can see this is a pulsed crest. You can see that it's just a crest. We can also have a pulsed trough if we wanted to. And you see the trough is just below the bottom. And in case you're unfamiliar with the terms, a crest is the top part of the wave, the maximum positive displacement, the maximum positive amplitude. And the trough, you can see down here, is the bottom. Then we have what we call traveling waves. Sometimes they're called progressive waves. And this is when the oscillation that causes the disturbance occurs over and over and over again, and you get both crests and troughs. And so to quickly model that, you can see how we now have crests and troughs occurring, and the wave is traveling from left to right. And this is what we call a transverse wave. We'll talk about in a second. But notice that the medium is oscillating back and forth. It's not actually moving in the direction of the wave. Okay, and so to kind of define that, we have our transverse waves. The medium's disturbance is at right angles to the direction of wave propagation. So our wave is traveling here from left to right, but the displacement of the medium itself is up and down, as you can see that. Here we're just showing you create a transverse wave, say in a spring or a string, by oscillating your hand up and down, and you get the string or spring or whatever it is moving up and down, but the actual energy itself is traveling to the right here. And in our transverse progressive wave here, if you look at these little white dots, those are representing the material of the medium. You can see this one in particular is oscillating up and down. It's not actually moving. It has no net movement really over the course of the wave's progression. It goes up and down, but it's oscillating back and forth around this equilibrium position along this median line. But if we follow the crest, we see the energy. The energy is represented by the crest. The higher the crest, the larger the amplitude, the more energy the wave has. But these particles are simply being displaced back and forth across this equilibrium position. So our definitions: The crest is the point of maximum positive displacement. The trough is the point of maximum negative displacement from equilibrium. And those values, the magnitude of those values, the magnitude of those amplitudes should be the same. The magnitude of those displacements should be the same. They should be the same as the amplitude of the wave. Transverse waves can't propagate through fluids, which are our gases and our liquids. It doesn't work. The way that the energy has to be transferred through those particular mediums. It has to be transferred through a solid where the particles are actually connected to each other. If the particles aren't connected to each other a little more rigidly than they are in fluids, transverse waves can't propagate through them. Water waves are technically surface waves. They're a little bit different. They're not really transverse waves. And then we have our longitudinal waves. And longitudinal waves are ones in which the medium oscillates in the same plane. And so here our energy again is traveling from left to right, but our medium is oscillating back and forth in that same plane. It's oscillating back and forth from left to right. And when it oscillates back and forth, what you end up with is, if we're talking about here, you have some of the medium oscillating here and some of it oscillating over to this side. And so you end up with these areas where there's not much medium, and those are called expansions or rarefactions. And then you end up with areas where the medium is all condensed, where it's really compressed and it's tight together, and those are called compressions. The expansions or rarefactions are similar to our troughs in our transverse waves, and our compressions are similar to our crests in our transverse waves. We can take a look at compressional waves. Let's look at a pulse first. And again, this is just a single compression, and you can see it's moving down from left to right. Here it comes along the path. And if we change the amplitude in a compressional wave, the amplitude is directly related to the density of the material in the compression, or the lack of density, I guess you could say, in the rarefactions. And so let's do a progressive wave here. And here's our frequency. And you can see how those compressions are the darker spots because there's more material. How those compressions move from left to right. And that's the energy. If we pause it real quick, you can see in this area where the material is much more compressed. But then if we look at this area over here, the material is more spread out because it's still the same amount of material. So if it's compressed in one area, it has to be rarefied or expanded in the other area. And so the amplitude in a longitudinal wave really is a measure of the change in pressure or the change in material density from the equilibrium position. And so if the compressions are twice as dense as how it would normally be, then the rarefactions should be half as dense. And so similar to the amplitudes of crests and troughs in transverse waves, the amplitude of the change in densities for compressions and rarefactions in longitudinal waves should also be the same. And we mentioned this. Compressions are the maximum density, rarefactions are the minimum density, and those changes should be the same. So let's talk about the periodicity of our waves. And What this means, we're talking about periodicity, is that the displacement varies periodically, and it varies periodically both with time and with space. And so if we first look at the, let's zoom out a little bit, the displacement space graph. This is a graph. Let's imagine we're taking a snapshot. We call this a snapshot graph. You're looking at a graph at a specific point in time. You're creating a wave and you snap a picture of it, you snapshot it. This is essentially what you would see. If this is some distance, this is, let's say, 1 meter and 2 meters and 3 meters, you're seeing that graph, and this is at one specific time frame. So one specific time along the length of your wave, you have a series of crests and troughs. But it also varies with time. And so this is a displacement time graph. And here we're looking at a given point. We're looking at a specific point in time on this graph. And what that means then is that, oh, didn't mean to do that. We are looking at point P, and we're graphing the displacement of the material over a given time. So notice that on this axis, our x is time. And so after 1 second, the material has, or the matter has reached its maximum, and then it's going to start to come down. And so then after 2 seconds it's here, after 3 seconds it's here, after 4 seconds, after 5 seconds, whoops, that's 56, after 5 seconds it's back up to a crest. And so our period here, the period of this wave, is 4 seconds, because it takes 4 seconds to undergo one complete cycle. And it's important to be able to distinguish between the displacement time graph, which is what we have here, and the displacement position graph here, because our displacement time graph is at a given space. Our displacement space graph is at a given time. If we're looking here, actually let's switch to this particular graph. If we are doing a displacement position graph, we would say, okay, stop. We're taking a picture of this graph here, and you can see you have the entire length of the material that's creating the wave. And so you have a crest here, and a crest here, or crest here, and a trough here, crest here. We've just taken a picture of this at some given time. If we're doing a displacement time graph, though, I'm going to focus in, say, on this material right here in the middle. And I'm going to graph its motion over some given time. Now, I'm looking at a particle at the same position. It's this position in the middle, and I'm graphing its motion over time. Now when I graph that, you can see here how it's going up and down, up and down, up and down. When I create that graph, the graph is going to look like a wave because the particle's moving up and down. But the uniqueness is that we're looking at a time, or excuse me, a position over a period of time instead of a time over a position. And so that's kind of an important distinction to make here.